town A that has 10,000 people live in town A. And then over here you have town B. And in town B there's 1,000,000 people. Every year there's going to be, babies born. Some people are going to have babies. Here's my question. Which of the two towns do you think is going to have way more babies being born? Well, I think that's an easy question to answer, isn't it? Wouldn't you say that'd be town B, right? There's 1,000,000 people. You have a bigger population of people. Therefore, it can grow even faster. And that's the whole idea of this. And that can be modeled by the following differential equation. It says if y is a function of time t, the proportion can be written as follows. The rate of change of y is proportional to y. So this k right here is what we call the constant of proportionality. In other words, this is what's going to tell us how fast this thing's growing. Or actually, it could even be decay. Before I get to the most important slide, which will be the next one, I'm going to tell you that last year, when you were taking pre-calculus, and you maybe even did this in Algebra 2, I can't really remember, I think it's pre-calc, your teacher would have just said, here's the equation that you used to do these problems. Today I'm going to show you where that equation comes from. Okay? And you know what, guys? Do me a favor. On your notes, would you do me a favor? Change this dy over dx. Go ahead and just change that to dy dt. I was going to go with dx because that's what we're comfortable with. But if you guys don't mind, can we just do t? T is in terms of time, all right? T is time. So just go ahead and change that to t. So I'm going to do the problem the same way. So if I wanted to solve this differential equation, the first thing that I would do is I would separate the variables. Okay, so let's go ahead and do that now. Okay, so I'm going to make a little note here. I am separating the variables. Remember, one of the objectives was to solve or to separate simple variable differential equations. And so what I mean by that is if we look up here at our main differential equation, that has variables y, and believe it or not, there's a variable t. The reason we know there's a t is I had to add that t. It was x originally. K is not a variable. In fact, if you remember on that last slide, I said it was a constant, which means it's like 2 or 0.7 or whatever it is, but it's not variable. It doesn't change. So you'll notice that in this differential equation, I have a y variable over here, but I have a y variable over here on the right side too. That's bad if we're going to try to solve this, because you guys do not know how to do multivariable calculus. So what we want to try to do is get all the y's on the left and all the t variables on the right. So now notice that we only have y's over here, and over here the only variable is t. Okay, does that make sense? So now what we can do is now we can go ahead and integrate. So we can do the integral of dy over y equals, and then the integral, I'm highlighting some things here. Let's do it in green. K, and then dt. All right, so notice what I've got. The variable terms are y. Really, y is the only variable. K is a constant, so it can come out to the front. In other words, I could rewrite this as just the integral of 1 over y dy equals k integral of dt. Those last two integrals are exactly the same. I'm just using my properties of integration. And now we can go and integrate. We know what the left-hand side is, right? That's the natural log, absolute value of y plus. And I'm going to go ahead and write c1. And then when I integrate the right-hand side, I'm going to get kt plus, and I'm going to write c2 here. Now, I claim I don't have to write both of those, and I think I've already mentioned it before in this class, but I'm going to mention it one more time today. C1 is a constant, and C2 is a constant. Guess what happens when I add two constants together? Guess what you always get? A constant. So let's say that this constant was 5 and this constant over here was a half. If I take a number plus a number, I still get a number. So what I'm going to do now is I'm just going to write this as the natural log absolute value of y is equal to k times t plus c. Now if you want to call that c sub 3, you can. I'm just going to call it c. I claim that any constant plus any other constant is still a constant. In fact, I would say a constant times any constant is a constant. All right, now we're kind of stuck in pre-calculus. How do we get rid of the natural log when it's in a function? What's the inverse operation of natural log? Exponential function. So we are going to exponential both sides. I want to get rid of, I'm trying to solve this equation. I want my answer to be something like y equals something. So I want to get rid of that natural log. So I'm going to e both sides. All right, so that's going to give me the natural log. Absolute value. Oops, I'm sorry. Guess what happens to the natural log since I just used it? It went away. They canceled. So you get the absolute value of y equals e to the k t plus c. All of that's in those parentheses. Now stick with me here. I'm getting ready to do some subtleties that might make you feel a little uncomfortable, but hopefully I'll be able to explain that. I claim that the right-hand side is the same thing as this. Let me make a note here. I'm going to erase this, but you guys would all agree that x squared times x to the third is the same thing as x to the fifth, right? So I could say that x to the fifth is the same thing as x to the second times x to the third, agreed? Or another way you could think about it is this. Instead of this 5 here, I can say that that's 2 plus 3, agreed? Does this last step now make sense? So what I did is I took this exponent that was an addition and I broke it into a product. Hopefully that makes sense. That's a rule about exponents. And that's wonderful because, a few minutes ago I said that a constant plus a constant was a constant. Anybody want to take a guess on what a constant raised to a constant is? Constant. It is a constant. In other words, guess what e to the c is? It's just another c. Uh-oh. Things are starting to look good here. Last thing I need to do is get rid of these absolute value symbols. But guys, when you get rid of the absolute value symbol, is plus or minus, guess what the plus or minus of a constant is? It's just a constant. I hope this formula looks familiar to you. I hope somewhere in your mathematical life a teacher exposed you to that, because that is the formula that we're going to use on almost every example we do today. I just showed you where it came from. Your teacher in the past would have just said, hey guys, whenever you do any problems involving exponential growth or decay, just use this. They didn't show you the derivation. Yeah, I just used the calculus word there. So here's the important slide right here. Theorem 8.1, or I'm sorry, 5.1. Exponential growth and decay model. If y is a differentiable function of t such that y is greater than 0 and y prime is equal to k, by the way, this right here is that dy over dt equals ky. That's that differential equation I just solved. Then this right here is the solution for it. The initial value, c, is the initial value. By the way, that's, oops, if I can spell value, that's written right here. C is the initial value. K is the constant of proportionality. I already mentioned that. If K is greater than 0, it's going to represent growth. And if K is less than 0, it's going to represent decay. I'm going to do an example of both today. In fact, I'll do more than an example of both today. Now guys, I kind of went through that really quick, but let me just go back and hit this last slide one more time. What I did right here is I found the general solution for any differential equation like this. I used simple separation of variables to solve that differential equation. And that's where this comes from. It is the solution to this differential equation. So let's just go ahead and look at a problem. An experimental population of fruit flies increases according to the law of exponential growth. There were 100 flies after the second day of an experiment and 300 after the fourth day. Approximate how many flies there were in the original population. So I'm telling you right now, first of all, as soon as you see this, by the way, there's other things that we could have said here. We could have said that the growth is proportional to the size of the population. That would have also been a clue. So that tells us we can automatically jump that we know we're going to need this equation to find the answer to our problem. So we know a couple of things. Let's write two equations. I'm going to do this one in blue. It says after the second day there were 100 flies. In other words, 100 is equal to CE to the 2K. Notice that I changed T to 2 days, and I changed Y to 100 because 100 was how many flies there were at the end of the second day. I'm going to write another equation based on this information in green. After 4 days, there were 300 flies. Again, notice I changed Y to 300 and I changed T to 4. This is the only information that's given in the problem. The question is asking us, what was C? What was the original number of flies in the population? So I have equation 1 right here, and then I have equation 2 over here. Well, what can I do? Well, what I can do is try to see if there's a way that I can maybe substitute, because I got an unknown here and I got an unknown here. If I could somehow substitute stuff in, then we'd be okay. Well, okay, let's see if we can do that. Would you guys agree? Let's do this in blue just to be consistent. C is the same thing as 100 divided by e to the 2k. Actually, we got two variables, don't we? C is a variable and k is a variable. Now, what I can do is I can take that and put that in for C in the second equation. So let's go ahead and do that, and I'll try to do a good job with my notes here and not make any careless mistakes. And now what I'm going to do is I'm going to plug in 100 over e to the 2k, and then I'm going to raise that to the 4k. Don't forget the E, Mr. Allen. There's an E in there too. So all I did is I put this C in for that C. By the way, those C's are the same C. The initial amount of flies. Now, let me make a little side note here. Actually, here, let's just show the word. First of all, would you guys agree I could divide both sides by 100? Hopefully you would see that, right? Because there's 100 here and there's a 300 there. I can divide that over and make that 3. So then that leaves us with e to the 4k over e to the 2k, right? Does anybody know what e to the 4k over e to the 2k has to be? It has to be e to the 2k. Let me show you an example of how I know that that's true. What is x to the 5th over x to the 3rd? That's x to the 2nd, right? You just subtract the exponent. So that's what we did there, okay? Now I'm just throwing that out. I'm just going to let you guys know, I feel very comfortable with all these exponential rules. We're also going to be doing logarithmic rules here in a few minutes. I feel good about those. Maybe you do not. And again, I want to get rid of this e. So now what I'm going to do is I'm going to natural log both sides. I'm going to natural log the left-hand side, and I'm going to natural log the right-hand side. Natural log is the inverse operation of exponential. So that is going to give me the natural log of 3 equals 2k. Therefore, and I'm running out of room here. Do I have room on the next slide here? Awesome. Let's go ahead and go to the next slide. So then I'm going to get that k is equal to the ln of 3. And I think that's over 2, isn't it? Yeah. That makes sense? And by the way, just to let you guys know roughly what that is as a decimal, it's roughly 0.5493, but there's more to it than that, okay? So that's k. You know, and I guess another way we could have written this using our rules of logarithms is this is the same thing as 1/2 the natural log of 3, right? So that'd be the same thing as the natural log of the square root of 3. All of those are exactly the same value. Okay, so now I've got k. My question, though, has not yet been answered. And it is, what is c? Well, now we can figure it out, right? I'll just use this equation right here, and I already know what k is. That's going to allow me to figure out what c is. So now we'll go back to the first equation, and I'm going to say 100 equals, and then it's going to be c e to the ln of the square root of 3 times, I think it was 2, wasn't it? Wasn't it 2k? Yeah. So this was back from the first equation. This was the first equation, and I just substituted that in for k. Now, here's where I'm going to grab my calculator. I hope you got your calculator too. You should definitely practice this right now. If last week when you were taking the test, you realized you don't know how to use your calculator, now is a good day to ask Mr. Brown how to do stuff with your calculator. And C is going to be 33 and 1/3. I'm cheating here a little bit. I already did the problem. So the answer is about 33 and 1/3. We'll just round that to 33 fruit flies. Now, guys, guess how much calculus I did in this example? 0 calculus. There was no calculus on this problem. In fact, doing this problem reminds me back when I used to teach pre-calculus a long time ago. In case you're curious when the calculus happened on this slide. This slide right here, I did the calculus that we're going to use for the rest of the slides. In fact, I'm pretty much only going to do one more example of calculus-y stuff here in just, I think, our final example. Any comments or questions on this example on fruit flies? Hopefully that was a fruitful discussion. Okay. Going to move on then. All right. Oh, by the way, this is the graph of that. That looks really good. Sorry about that. This is that graph right here of this curve. This graph right here. You'll notice that right here, our initial value is 0.33 approximately. That's where that 0.33. So this was our answer. Here's our answer. Here was, after 2 days, there was 100 flies. And then after 4 days, there was 300 flies. So this curve right here, this curve can be modeled by y equals 33e to the, I think it was the ln of the square root of 3, if I'm not mistaken. That's this curve right here. Okay? All right, let's look at our next example. This one I'm actually going to let you guys try to set up on your own. I did that first one all on my own. I didn't do any calculus. I'm basically just reviewing stuff that you've probably been taught in the past. If you haven't, that's okay. So I guess I should come back to this. One more thing real quick. You remember here where I said that k was equal to 1/2 the natural log of 3, which is the same thing as the natural log of the square root of 3, which was 0.5493. Would you guys all agree that that value of k is greater than 0? And since it's greater than 0, that tells us that this is an exponential growth, which makes sense. Fruit flies grow exponentially. If you leave them alone, they're going to multiply very quickly and grow out of control. It's kind of gross if you don't like flies. You do like flies, and that's great. Okay, so this one is a declining sales, so this must not be growth, but the opposite of growth. I'm going to just read it to you, and I'd like you to see if you can figure out the answer on your own. I'm telling you right now, that very important equation that I wrote, y equals something, that I said we're going to use on almost all the examples today, is what you're going to use. It says 4 months after it stops advertising, and manufacturer company notices that its sales have dropped from 100,000 units per month to 80,000 units per month. The sales follow an exponential pattern of decline. What will the sales be after another 2 months? So will you please try to set that up? I'll give you a hint. This is very similar to the last problem. You're going to have to figure out some things like C and K and all those things, and then you'll be able to hopefully figure out your final answer. If you don't mind, I just launched a poll question. Should be very easy, I think. If you would answer that, I'd appreciate it. Okay, so hopefully you figured out what K was. K is going to be the natural log of 0.8 divided by 4. Because the question says, or the problem says, after 4 months, it went from 100,000 to 80,000. By the way, if you want to write that as 80,000 and 100,000, you can, or you can divide. In fact, you could have just written 8 and 10. It doesn't matter. It's still the same ratio, right? You'll get that for K. And just to let you know what the K value there is, it is approximately negative 0.0557858878. And let me make a comment here, a couple of comments. Comment number one, that is less than 0. Very important observation to be made here, because we said that if it was decay or a decline, it has to have a K value that's less than 0, which it does. Second observation is, you see this right here? I would store that in my calculator. I hope you know how to use the store feature of your calculator. All you do is once you get the decimal, there's a little button down here by the 1 button that says STO. You press that button, and then you hit the alpha button, that's the green button, and you pick whatever letter you want to store that in. You can store multiple decimals, and then that saves you from having to retype the decimal all the time. So then finally, once you have this, we now know that this is going to be y equals 100e to the ln of 0.8 over 4 times t. So that's our new equation. And to figure out our final answer, it says after 2 additional months, so change that t to a 6. Because we already had 4 months and we want another 2 months, so that's going to make it 6. So that's one way to do it. Your final answer here is going to be 71,554 units per month. There's your final answer. My answer is going to be a little bit more accurate than the one that they give in the text. In fact, if you look at the next slide, I've got another graph there. And when you look at that graph, you'll notice on their graph, it doesn't say 71,554, it says 71,500. That's because they rounded this decimal down here. And I choose not to introduce round off error. I leave the round off for the very last step of the problem, which I think is a good practice. Hopefully you guys are familiar with round off error. Don't round until you have to, which is the very last step. Okay? Any comments or questions on this example? I hope you were able to figure that out. Okay. Let me see how you guys have done on that poll question there. We're ready for our last example, though, so that's good. Last example is kind of the hardest example, but it'll be okay. Everybody got the poll question right this time. Yay. Last period, I did not get everyone to get it correct, so that's good. Okay, last question. Here we go. And then we'll try to do a little bit of practice, and I'll give you an answer. So it says, let Y represent the temperature in Fahrenheit of an object that in a room whose temperature stays a constant 60 degrees. The object cools from 100 to 90 degrees in 10 minutes. How much longer will it take the temperature of the object to decrease to 80? Now this problem is going to require us to do a little bit of calculus, because we're going to have to apply Newton's law of cooling. The differential equation here is a little bit different. I'm going to write dy dt, and again I'm going to note that t is in time, and in this case let's say minutes. And this is going to be equal to k times 60 minus y. Oops, I did that backwards, sorry. Not 60 minus y, y minus 60. Hopefully you understand why that is. The object's not going to go below 60 degrees, right? That is the room temperature. So whatever, so if it's 100, it's relative to the 60, it's only 4 off or 40 off from. Does that kind of make sense? So this is a little bit different So I am going to do a little bit of calculus. We're going to do basically the same calculus we did earlier, which means the first thing I want to do is separate my variables. So remember, our first objective here is to know how to do basic separation of variables. So again, the only two variables here are t and y. T and y are the only two variables, so let's go ahead and separate those. So I'm going to say dy over y minus 60. I'm cross-multiplying. I just cross-multiplied. So now you'll notice that the variable y is all on the left, and the variable t, which is just this dt, is on the right. So next up, we can go ahead and come over here, and we can say that this is going to be the integral of dy over y minus 60 equals the integral, and I'll go ahead and put the k out to the front. Now we're going to undo the differentiation. So that left-hand integral, that looks familiar. We've done that one. We did an entire section in our book on it. And the right-hand side is going to be kt plus c. Now notice here I didn't put c1 and c2 like I did on the last one. Oh, by the way, I have another poll question for you. It's a really, oops, I just ended it. Oh, well, let's not worry about it. Okay. So, how do I get rid of the natural log? Exponential. So we're going to exponentiate both sides. So we're going to e this side, we're going to e that side. That is going to give us the natural log, absolute value of y minus 60 equals, I just did it again. Guys, what happens to the e and the ln? They cancel, they undo each other. This e and this natural log, that just leaves us with the absolute value of y minus 60. Then over here, we're going to get c e to the kt. Again, I'm kind of combining steps that I did separately last time to kind of speed this process up. If I get rid of the absolute value, that doesn't change the c. C is still some arbitrary constant that we have not picked. And then so finally, we get the following equation. And this is the equation that we're going to use for this problem. I'm going to put it in a box here. Again, it always does that kind of weird extra extension there. Sorry about that. This is our general solution. Here is our general solution for this problem. It's a little bit different than the last one. The only difference really is that plus 60, which again kind of makes sense. All right, so I'm going to go to the next slide. I'm going to need some more room here. So again, we have y equals 60 plus ce to the kt. Now we know that in this problem that at t equals 0, y was 100. Do you guys remember that? It says it cools from 100 to 90 in the first 10 minutes. So we know that initially it was 0, 100 for the temperature. In other words, I can now substitute this stuff into this green equation to figure out what C is. In fact, I'm going to do that now here. Hopefully if I can hit the right buttons. Equals 60 plus CE to the K times, and then I'm going to put a 0 in there for our T value. Okay, so that's going to give us 40 equals C to the 0. So C is clearly just 40. In other words, our equation now is y equals 60 plus 40 e to the kt. So I just found C. In fact, let me circle that. I figured out what C was. That was our initial condition. Based on the initial condition of 0, 100, I figured out what C is. Please make sure you get this step. I actually kind of screwed that up last period in my explanation. I got it right this time. That's good. All right, now I'm going to figure out what K is. How I'm going to find K is I'm going to use this second part. I know that, in fact, let's do it again in red. I know that at 10, it was down to 90 degrees, right? This is the T, this is the Y. So now I can substitute all of that in here. In fact, let's do that. That's going to give me 90, and then I'll do everything else in purple, equals 60 plus 40 e to the k. And then the only thing that's going to be left here that's in red is going to be t, which is 10. So now here's where I'm grabbing my calculator, because I want to make sure I don't make any careless mistakes. I'm going to minus 60, that's going to make it 30. Then I'm going to divide by 40, that's going to make it 3/4. So that gives me 3/4 equals e to the 10k. Now I'm going to natural log both sides. So I'm going to do the natural log on both sides. I'll go and leave this other stuff in red. So this is going to be 3/4 equals, and then e to the 10k. And guess what happens to the natural log and the e? They cancel out again, so you're going to get 10k equals the natural log of 3/4. So k is equal to the natural log of 3/4 divided by 10. And just to let you know what that decimal is, and this is something I would probably store in my calculator, is as follows. Negative 0.0287682. I'm going to stop there. It goes on. So now I have K. In other words, Y equals 60 plus 40 e to the negative 0.2. Oops, there's another 0 in there. 287682t. This is the particular solution that I'm looking for. That will be this equation right here. I just went through how to find that. By the way, my answer is more accurate than the one on the graph. Oh, I guess I should know. I still haven't gotten the answer yet. I haven't done the answer yet. The question is, how much longer will it take the temperature of the object to decrease to 80 degrees? So that means, and now I've got to kind of do this last part. I guess I'll do it kind of up here because I'm running out of room. I should have given myself a different slide. Let's do a different color than we've used thus far. Let's just do black. So I want to know if y is 80, because that's the question. If y is 80, and that's 60 plus 40 e to the negative 0.0287682t, you've got to solve that equation. Now the only thing left is the t, and t here turns out to be 24.094. Which, by the way, you'll notice that that matches up with what's on the graph. And now we can finally answer the question. And the question is, how much longer? You want to say this is the answer, but that would be incorrect. How much longer? Well, remember the last known point was at 10 minutes, correct? So how much longer is 24 compared to 10? 14.094 minutes. That's your final answer for this problem. That was a fun one, wasn't it? Now my hope is that as I went through these examples, you were sitting there, hopefully your spidey sense was going off and you were saying, I kind of feel like I've done some of this stuff before. The answer is if you have, which you should have. I just put the exit ticket in the chat. We are now we're about 5 minutes away from our time being up. But I'm going to give you the option. First of all, I need everyone to complete the exit ticket. I'm going to take questions, and I've got an activity, a fun little activity here at the end. If you'd like to participate, I think you might find it fun, and it might even help you with your homework today. Does anyone have any questions on my last example? Okay, I'm going to stop recording.